Okay, let us look at the four variables that we were examining with gas laws. We had pressure, volume, temperature, and N, or the number of moles. And we had the different scientists who studied some of these variables and how they related to each other. So Boyle, he held the temperature and the number of moles of a gas constant, and he varied pressure and volume. And that's how you conduct experiments, right? You try to hold everything else constant and you measure how two variables relate to each other. And he found out that pressure was inversely proportional to volume, or the way he's in other words, if pressure goes up, volume must come down, correct? Now, another scientist, right, that we've talked about in detail is Charles. Charles, he did another experiment, and this time he decided that he wanted to hold pressure and the number of moles constant, and he wanted to vary temperature and volume. And remember, this is the Kelvin temperature. The Kelvin temperature and volume, and he found out that the Kelvin temperature is directly proportional to the volume of something. In other words, if the Kelvin temperature increased, the volume should also increase. Okay? Now, Avogadro, he came in and he held pressure and temperature constant, and then he varied the volume and the number of moles. And he also found out that volume was directly proportional to the number of moles of a gas. So in other words, just kind of like, remember the balloon example that we talked about. If you pump more gas molecules into the balloon, the balloon will expand and take up more space or increase the volume. Just like the more people that you have, the bigger that room that you need to fit all these people, correct? Alright, so then this brings us to putting it all together. And if we put this all together, we come up with something like so. That volume is directly proportional to the number of moles and the temperature, but inversely proportional to pressure, correct? Now, what we're going to do is we're going to replace this proportional sign with an equal sign, but when we do that, we have to multiply by a proportionality constant, R. And this R is our gas law, or our gas constant. And this is a number given. In other words, if we bring P here, PV equals N over T will always give you R. So if you take pressure times volume and divide it by N times T, you will always get this constant R. Alright? And we use that to our advantage to figure out the some unknown compounds, some unknown gases. Alright? But what is this R, you may say? And that is going to be given to you on the exam, but R is 0.0821 liter ATM per mole K. And it has a lot of units, and these units are extremely useful because your pressure should be in ATM, your volume should be in liters, your N in number of moles, and your temperature in Kelvin. Otherwise, you will not be able to use that. And actually, R comes sometimes in a different number if you had different units. But this is the one that's in your book, and this is the one that we're going to use. So you have to, if you want to use this R, you have to convert all your variables to these associated units. And so this is the way that we write if we want to rearrange this algebraically, you can memorize the ideal gas law as PV equals nRT. Okay? So this is how you want to memorize the ideal gas law. Now, why is the ideal gas law different than the combined gas law? Remember, the combined gas law, P1V1 over T1 is equal to P2V2 over T2. Here, we don't have N, okay? So, in the ideal gas law, we add N to our equation here. And so we're able to vary the number of moles, not just the volume, pressure, and temperature. Here, for the combined gas law, N was held constant. Okay? And then we had three variables that we were measuring. Okay? But here, we can have all four variables of our gases: pressure, volume, temperature, and the number of moles. Okay, let us see how we can use the ideal gas law. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atm and a temperature of 315 Kelvin. Okay, so let's collect our information. We want to calculate the volume, so we don't know what that is, and we have 0.845 moles of nitrogen gas at a pressure of 1.37 atm and a temperature of 315 Kelvin. See, you have V, N, P, and T, all four variables, so it looks like you're going to be using the ideal gas law. That's how you know which law to use, depends on the variable that you're given, right? So PV is equal to nRT. Perfect. What is R? 0.0821 liter atm per k mole. Okay? And so we have to make sure that all of our units are lined up before we can use this R. Alright? So is N in moles? Yes. Perfect. Check. Is P in atm? Yes. Perfect. Is temperature in Kelvin? Yes, check. So whatever we have left is the unit for volume, and so that should end up being in liters. Now, let us solve for this volume. Volume, then just divide by P on both sides, and let's plug in N, which is 0.845 moles, times R, which is 0.0821 liter atm k mole, and I suggest that you do write those units, so because you will see how they will cancel out. 315 Kelvin, and we have pressure here on the bottom as 1.37 atm. Perfect. So check this out. The moles cancel, the kelvins cancel, the atms cancel, and I'm left with liters, and liters is a unit of volume, so great. That means I'm doing it right. Okay, 0.845 times 0.821 times 315 divided by 1.37, and so it's 15.951, but we're going to do it to 3 sig figs, so that would be 16.0 liters is our volume. Okay? Okay, now here, let us calculate the number of moles of a gas in a basketball inflated to a total pressure of 24.2 psi and a volume of 3.2 liters at a temperature of 25 degrees Celsius. And we want to figure out N, the number of moles. And so, because we have all four variables here, we have 3 unknowns and 1 unknown, we are going to use our ideal gas law. And remember, R is 0.0821 mole, liter atm per mole. Okay, so we are trying to figure out what N is, so let's divide both sides by RT. So N is PV over RT. And the pressure here is in PSI, but we want it in ATM because we want to match all our units to the units for R. So we have to convert 24 PSI, 24.2 PSI into ATMs. And according to your table 11.1, for every 1 ATM we have 14.7 PSI. Is that right? So 24.2 divided by 14.7 is 1.65 ATM. Alright? Next, let's look at our volume. Is our volume in liters? Check. Perfect. So we don't have to worry about that. Temperature is in Celsius, but we want it to be Kelvin. So temperature is 25 degrees Celsius plus 273. That's 298 Kelvin. Perfect. Alright, and of course N is going to be in moles. Now we can plug everything in. So let us continue on our way here. So N is P, which is 1.65 ATM, times volume. And what was our volume here? 3.2 liters. Divided by R, which is 0.0821 liter ATM per mole K, and multiplied by our temperature, which is 298 Kelvin. So the Kelvins cancel, the ATMs cancel, the liters cancel, and perfect, we're left with moles, and that's exactly what we are looking for. So 1.65 times 3.2 divided by, and then we're going to close the parentheses on the bottom, times 298. So you should have gotten 0.216 moles of air in that basketball. Okay? Does that make sense? Go ahead and try a couple on your own and then replay the video to see if you are correct. Okay. Go ahead and try this one on your own first and then see if you get the correct answer. A 8.5 liter tire is filled with 0.55 moles of a gas at a temperature of 305 Kelvin. What is the pressure of the gas in the tire? So let's collect our information. V1 is 8.5 liters, N is 0.55 moles, and the temperature is 305 Kelvin. And so what is the pressure? So we have 1, 2, 3, and we're trying to figure out the fourth variable. That means we should use PV equals nRT. And R here is 0.0821 liter ATM per mole K, right? So let us try to solve for pressure. To solve for pressure, just multiply or divide volume on both sides. So your N, is it in moles? Yes, because it has to be in moles on both sides for us to be able to use this particular gas constant, okay? Now, temperature is in Kelvin, perfect. Pressure is going to be in ATM because that's what we are going to find out. And volume, is that in liters? Yes, it is. So it's all perfect. We don't have to do any conversions. Okay, so let us now just plug everything in. 0.55 moles times R, which is 0.821 liter ATM per mole K, times temperature, which is 305 Kelvin, divided by volume, which is 8.5 liters. So your pressure should be in ATM because look at this, your moles cancel, your liters cancel, your kelvins cancel, and you're left with ATM. So your pressure is going to be in ATM, 0.55 times 0.0821 times 305 divided by 8.5. And so you should get 1.6 to 2 sig figs because of this number here. 1.6 atm. And so that is the pressure of your tire. Alright, how much volume does a 0.55 6 mole of a gas occupy when its pressure is 715 millimeters of mercury and its temperature is 58 degrees Celsius? Go ahead and try this on your own and see if you get the correct answer, okay? So, volume is unknown, N is 0.556 moles, pressure is 715 millimeters of mercury, temperature is 58 degrees Celsius. Because we have N, P, T, and we're trying to solve for V, we have to use PV equals nRT. So R is 0.0821 liter ATM per mole K. Alright, and so what do we have here? We are trying to solve for volume, and we can rearrange the equation and divide by pressure on both sides to get volume alone. Okay? Now, let us do our check to make sure all of our units for our variables match our units for R. Moles are checked. Pressure, however, is in millimeters of mercury, and it should be ATM. That means we're going to convert 715 millimeters of mercury into ATM. And according to your chart, there's 760 millimeters of mercury for every 1 ATM. So 715 divided by 760 is 0.941 ATM. So that's our pressure. Our temperature is in degrees Celsius, but as we know, we need to convert it into Kelvin. So 58 plus 273 is 331 Kelvin. Now all of our units line up, and our volume hence should be in liters. Okay? So let's plug everything in. N is 0.556. R is 0.0821 liter ATM per mole K times our temperature, which is 331 Kelvin. So let's put this on the side right there. Divided by pressure, and our pressure is in ATM. So you see your ATMs cancel, your moles, forgot to put a mole here, your moles cancel, and your kelvins cancel, and what are you left with? Liters. And so let's do 0.556 times 0.0821 times 331, and that number divided by 0.941. So we should end up with 16.056, but we will call that 3, yes, we will have 3, or actually 2 sig figs because of this. So it'll be 16 liters of gas, and that is our volume. Now we're going to see how we can find the molar mass of a gas from the ideal gas law. And this is actually very useful for chemists. If we don't know the identity of a gas, we can find out using this technique. So use the ideal gas law in combination with mass measurements. A sample of a gas has a mass of 0.136 grams, and its volume is 0.112 liters at a temperature of 298 Kelvin and a pressure of 1.06 atm. Find out its molar mass, and I'm going to call that molar mass is unknown. Well, we're given PV equals nRT, and we're given that R is 0.0821 liter atm per mole K, but we don't have mass in this equation. We have N, which is the number of moles. But remember, guys, what is the definition of the number of moles? How do we figure out the number of moles? Don't we always take the number of grams and divide it by the molar mass of a substance? So if we were trying to figure out, how many moles is 12 grams of hydrogen gas, remember, we take the grams, and we know that there's 2.02 grams of hydrogen gas for every 1 mole. So you see how we're taking the grams and we're dividing it by the molar mass of hydrogen gas, and so we get the number of moles. So with this definition, it'll be perfect to figure out how to get the molar mass if we have the grams. We have the grams, but we don't know what molar mass is. So we can rewrite it like this: grams per molar mass times RT. And we have grams, we have R, we have T, we have P, and we have V, so we have only one unknown. Okay? So you can either write it this way, okay, and then we'll just solve for molar mass by multiplying on both sides and then dividing by PV. Okay, so it'll be grams RT over PV. Does that make sense? So now we have our number of grams as being 1.36 grams. Okay, and then we have our R as 0.0821 liter atm per mole K, and we have our temperature as let's see, what is our temperature here? 298 Kelvin divided by our pressure, which is 1.06 atm, and our volume, which is 0.112 liters. We can go ahead and cancel out ATMs, liters, and we'll keep the moles because this is going to be grams per mole, which is the unit of our molar mass. See, we can't cancel out moles. And then the Kelvin. So isn't that perfect? The grams per mole is left over. Grams per mole is a unit for molar mass, so it all works out. Alright, so let us go ahead and multiply this out. 0.136 times 0.0821 times 298 divided by, and we want to put the bottom in parentheses, so we end up with 28.02 grams per mole, which is the unit of molar mass. Okay? And sometimes we can use this to find out what the identity of that gas is. It could be N2, you know what I mean? Because N2 is got 14.01 times 2 molar mass. It's 28.02 grams per mole. So it could be that. But sometimes there's different combinations, so you can't be 100% sure, and there's different ways we can confirm our conclusion. Alright, go ahead and try this next example. A sample of a gas has a mass of 827 milligrams, okay, and a volume of 0.270 liters at a temperature of 88 degrees Celsius and a pressure of 975 millimeters of mercury. And we want to find the molar mass. And the molar mass, of course, is in grams per mole. So we want to use our ideal gas law. So let's write our gas constant here. Alright, and let's see what we're given. We have PV equals N RT. I keep writing it like that. Alright, nRT. Alright, and so we are given the volume in liters. Perfect, so those match. Alright, we're given the pressure here, but the pressure is not in, these don't match. So let's convert the 975 millimeters of mercury into ATM. And we know for every 1 ATM we have 760 millimeters of mercury. So 975 divided by 760 is 1.28 ATM. Perfect. Next. Okay, now where were we? Let us see. So we've converted our pressure into ATM. Let's look at our other units. And let's look at our temperature here. And our temperature is not in Kelvin. So our temperature is 88 degrees Celsius. Let's just add 273 to that. And 88 plus 273 is 361 Kelvin. Okay? Next, let us see what we got. So we have ATM, we have Kelvin, and we have liters, and the moles that we're going to use is to figure out the molar mass, correct? Because we start out with grams, and remember, N, we're going to just sub in for that. N is your number of grams over your molar mass. Okay, the only problem is that, you know, your molar or your mass should be in grams, not milligrams. So let us go ahead and convert 827 milligrams into grams. For every 1,000 milligrams, we have 1 gram. So this is going to be 0.827 grams. Okay? Now let's plug in everything. We had to do some conversions here. And again, we're solving for molar mass. So let's go ahead and solve for molar mass algebraically before we plug in our numbers. Let us multiply by molar mass on each side here. And then we'll bring the molar mass here. And then we'll divide PV here and bring PV over here. So then your molar mass ends up being grams times RT over PV, correct? That is your molar mass. Perfect. Now let's plug everything in. Our number of grams is 0.827 grams times R, which is 0.0821 liter ATM per mole K, times temperature, which is 361 Kelvin. Let me put a little line here, divided by pressure. And what is my pressure? 1.28 ATM. And times volume. And volume was, let's go back up here, oops, and see what we had. 0.27 liters. Okay, now let's see what cancels out. We have our ATMs cancel, we have our liters cancel, we have our Kelvins cancel, and what are we left with? Grams per mole. Perfect. The molar mass is supposed to be in grams per mole. So let's go ahead and multiply everything out. And we're going to divide by the bottom part, but you're going to close it off in parentheses. So you get 70.9 grams per mole. That's your molar mass. Okay, and